Hey, it's Mrs. Golding. I am in section 7.4, page 567, and I'm going to just roll out problems 22, 23, 25, and 26, okay? Just jumping around, but I feel like if I was sitting there with you, you might be like, why are you even going over these, Mrs. Golding? These are easy. I've got these, right? So you're cooking because you're like, what? 7 times 3 is 21, so G is equal to 7, right? Because you know that fact. The other one, you're like 6 times 2 is 12, so you know X must be equal to 2. And you didn't even you didn't use inverse operations. You didn't say 21 divided by 3 is 7 because you already know that fact. It's a fact family, as a matter of fact. Funny, right? Remember those triangles you did in elementary school? 21 divided by 3 is 7. 3 times 7 is 21. Okay? The deal is, this is easy, but when you get down here, 25, 26, you're like, somebody broke math, right? But it's not. It's not broken. It's just not a fact family. That's why it's a little harder. And here's what I want you to remember. Some people believe the moment something gets hard, that they must be stupid. They must be dumb. Not at all. When things get hard for us, it's just a chance for our brains to grow. And they do. Those neurons, the neurons in our brain, we can grow those pathways and we can make some of them even stronger when we're working at things and when we're trying to learn. So just because something's hard doesn't mean it's that you're dumb. Okay. We're going to use those inverse operations here. Now watch. We're going to divide both sides of this equation by 2 and 55 hundredths because we want to isolate the variable. We've been doing this a lot, so you're probably getting used to it. I'm going to then divide 17 and 85 hundredths by 2 and 55 hundredths. Now, to me, you know the algorithm says move this over twice, move this over twice, and we're going to push this up here, right? Before that was moved over, that looks to me like money because it's, I don't know, for me it looks like $2.55 times what is equal to 17.85, right? So I'd be thinking in my head, how many $2.55 is, or like how many D could be donuts. A donut, that'd be expensive donut. It must be enormous, right? A $2.55 donut. How many of them could I get for $17.85? See that? So I might in my head be thinking, instead of moving that over like the algorithm says, I might think 250 and then $5, and then I'm thinking 750, and then I'm thinking $10, right? $10 would be 4 donuts. I got more, right? Then 5 would be what? 10, 11, 12, 50. Then 6 of them would be what? 6, 250, 1250, 12. What is it? 6 times 250. I lost track. 1,000. Did you? $10? 1250. You got it? I don't know. But I think I want to try 6 as I'm going along, and I'm going to try it. Now watch, cool thing. If you put a 6 here and you test it out, you can multiply. 6 times 5, right, is 30. Now watch. I was just kind of making an estimate, wasn't I, in my head when I was doing all that? So 6 times 5 is 30. I'm going to put a little 3 up here. 6 times 5 is 30 plus 3 is 33. Carry another little 3. 6 times 2 is 12 plus 3 is 15, right? It's too small. But let's see how much is left. 8 minus 3 is 5. And do you see what's left? Exactly 255. So I know that I just needed one more. Okay. So D is equal to 7. Okay. All right. Check back with me and we'll do number 26.